All right, so here is our first example. So I had said when you're picking what to let u equal, you want to pick like the guts of the problem, like the inside stuff. Like if there's a square root, it's going to be the stuff inside the square root. Or if there's an e to the stuff, it's going to be that stuff. You know, the thing that's inside the function. Or the thing with the highest power. I'm going to add to that, if you aren't sure and you just have like no idea and you want to just guess, pick the denominator. So the guts of the problem, like the inside stuff, the highest power, or when in doubt, just pick the denominator if you have a fraction. Now, in this case, that is the stuff with the highest power anyway. But we're going to let u equal the x squared minus 10 part. And so that derivative is 2x dx. And I'm going to adjust with a 1/2. And so if you want to highlight, you can. Again, not like a requirement, but we're matching up the x and the dx. And again, it's going to match together. I'm not going to give you an undoable problem. So if it doesn't match, then you picked the wrong thing for you. You just have to go back and pick something else. So 1/2 goes out front, du goes at the end. Whatever you didn't highlight is still there. So we still have this x squared minus 10, which is u, but it's in the denominator. So it is 1 over u. And hey guys, what is that antiderivative going to be? I put it in the title, wink, wink. Yeah, good, ln. So don't forget to do this step. I was kind of putting a star next to it when I taught it, you know, when we did last time's notes. Don't forget to actually do the antiderivative, because I have people that'll skip that step. This is 1/2 ln of u plus c. And again, we put absolute value around that because you can't ln a negative number. And then last step, we're going to just put this statement back in for you. So your final answer, ln, or 1/2 ln of x squared minus 10 plus c. So that's not really like new information. It's exactly what we did last time. There was just an ln in it. Yeah, so again, buckle up, guys, because we're just going to do a bunch of practice problems here. I'll give us another break at some point in between. Just don't fade out on me here. All right, so again, if you aren't sure what to let u equal and you need to just get started on the problem, let u equal the denominator. So it's going to be cotangent of x plus 5. And so what is the derivative of that? I know it's difficult to type in the chat, but I still want to ask you this question, so just maybe do your best. I want to throw that question out there to you and allow the problem to help you. Derivative of cotangent. Here, I'll see if I can dig out my flashcards here. Your derivative of cotangent. Yeah, you guys are using the problem to help you. You're really, really close. Everyone that's, because some people are typing to me privately. Just one thing, because it's a co, what are we gonna have in front of that? Yeah, good, perfect. So negative cosecant squared. But this is where the problem is helpful because it's right there. You know, like it doesn't have the negative sign, but you know, you can use the problem to help you because everything's gonna have to match together. All right, so this derivative is negative cosecant squared of x. The 5 is a constant, so that's gone. And then dx. And we just don't have a negative, so we're just going to have to multiply by a negative to cancel that out. It's negative du equals cosecant squared of x dx. And you can call that like a -1 if that's your preference, if you want to have like a -1 in there. And then highlighting, we're going to highlight the cosecant squared and the dx. And so the negative is going to go out front. Again, you can put -1 if that's your preference. Du goes at the end. And whatever we didn't substitute out is still there, which is 1 over u. And so that antiderivative, same as what we did in this problem here, it's going to be negative ln of u plus c. And then we're going to put this statement back in for u. So your final answer is negative ln of cotangent of x plus 5 plus c. And this one is actually kind of similar to one that we did in the homework that had a square root in it. So we're going to let u equal square root of x. And so that derivative is 1 over 2 square root of x dx. And so that does match up in the problem. We have that square root of x in the denominator. We just don't have this 1/2. So to cancel that out, I'm going to multiply by a 2 to adjust this. All right, so the square root of x in the denominator, that matches that 1 over square root of x, and then the dx. And so in its place, we're going to put 2 du. And so again, whatever you didn't highlight is still there, which is cosine of u. And so again, don't forget to do the antiderivative. What is going to be our antiderivative for cosine? Like we need a function that if we did the derivative, we would get cosine. Like cosine is the answer. We want the question. Yeah, good, perfect, nice. And I got my flashcard right here. Derivative of sine is cosine. So this is going to be 2 sine of u plus c. And then you just have to put square root of x back in for u. So 2 sine of square root of x plus c.
Miss Cole.
Yeah, good.
When you highlighted, why did you highlight the square root of x on the bottom instead of the one in the numerator?
Because in our derivative here, that square root of x is in the denominator. It's a 1 over square root of x. If it helps to put the 1 there.
Okay, I see.
Sometimes like a simple thing, like just sticking a 1 in there can like help a lot. So we're replacing not a square root of x, but a 1 over square root of x. So this is the part that got substituted out. But it is tricky because there are 2 of them. But it was the one in the denominator that we substituted out there. So I'm going to do this one and then I'll give you guys one to try here. Now this one looks like a monster, But once you start substituting, like all the others, it ends up not being so bad because again, the point of doing the substitution is to take something that looks really complicated and make it look a whole lot simpler. All right, so we are gonna let u equal the most inside part. It's tricky on this one to pick, like, do we want the sine of the x squared or do we want the cosine of the x squared? We want the sine of x squared because that is being cubed. So that's like inside of a cubed function. It's like again, you want like the guts of the problem. This sine of x squared is being taken to the third power. So that's like what's inside the cubed function. So that's the inside part that we want. All right, and then derivative of that. So derivative of sine is cosine, but this one involves a chain rule. So derivative of sine is cosine, and then we have to chain on the derivative of x squared, which is 2x. So sine was the outside function and x squared was the inside function. So that was a chain rule there. And so I just saw a question in the chat, why don't you take the sine cubed? If you did take the sine, here, let me show you what would happen. And this is what I keep telling you guys, if you ever pick the wrong thing, you will always catch it because it simply will not work out. So let me show you what would happen if we like went down this rabbit hole. If we did this derivative, there would be 3 links in the chain. You'd have the cubed and then the sine. This is good, we're gonna go over this because this will review chain rule for you really nicely. We have the cubed and then the sine and then the x squared. So you would bring the 3 down. It would change to sine squared of x squared. And then derivative of sine is cosine. And then derivative of x squared is 2x. So you would have 3 links in the chain. And then when you go to match it up, you don't have a sine squared anywhere. Like there's not a sine squared anywhere in this problem. So it's not going to match up. Like it's just not there. And then you would be like, oh, that didn't match. So I need to go and pick something else. So that's what I keep saying. If you pick the wrong thing, when you go to like find this in the problem, it won't be there. And it's almost like self-checking, which is kind of nice. Right, so this one, we have the cosine of x squared, and we have the x. There's this little x out front here. What we don't have is the 2. So I'm going to adjust this with a 1/2. And then watch what happens in this. This is really beautiful. We end up highlighting almost the entire thing. Like the problem sort of disintegrates. It's like awesome. It all goes away. So we've got the cosine of x squared. That's getting substituted out. We've got the x. That's getting substituted out. And also the dx. And so look, I highlighted like almost the whole problem. So that's all going to go away. And in its place, we're going to put 1/2 du. So 1/2 goes out front, du goes at the end, and whatever we didn't highlight is still there, which is this sine of stuff cubed. So that is going to be u cubed. And so once again, the whole point is you took something that looked awful and really made it look a whole lot simpler. So don't forget to do the antiderivative. For u cubed, that would be 1/4 u to the 4th plus c. And so 1/2 times a 4th, this will be 1/8. And then I just need to put this sine of x squared back in for u. So it is that stuff to the 4th. So it is sine to the 4th of x squared plus c. And I did see another question pop up. I was just mid-sentence, so hold on a second. I'm going to answer that. It be sine of u, because we let u equal sine of all that stuff. If we had let u equal just the x squared, well, it wouldn't have worked if we had done that. But if u was just the x squared, then it would be sine of u. But u was the entire statement. It was all of this. And remember, this means sine of x squared cubed. That's what this means. When you see that cubed there, it's the whole thing being cubed. So like this is u to the 4th, It's this entire thing to the fourth. Did I answer that question sufficiently? I tend to keep on like rambling if I don't get a like, oh, I've got it now. Okay. I'm going to give you guys one to try. And then I will go over it. I'm going to give you one with boundaries because I believe you guys can handle it. All right, so I'm going to pause the recording and just give you like a few minutes. Give that one a try, and then I will go over it for you. I didn't give you one that had trig. All right, guys, let me go ahead and go over this one for you. So what did you guys let u equal for this one? What did you pick? Yeah, good. Like the denominator. Yeah, the thing with the highest power, or when you're not sure, just pick the denominator. Perfect. All right, so that derivative is 3x squared dx. And what are we going to have to do to adjust to make it match the problem perfectly? Good, nice job, guys. Times 2, perfect. Multiply by 2, you rock. All right, so that would be 6x squared dx. And so when I go to highlight, that's going to match exactly. And so 2 goes out front, du goes at the end. What's still there is u, but it's in the denominator, so 1 over u. And then we have to adjust the boundaries. So if we plug in 0 here, we're going to get 4. If we plug in 3 cubed is 27, plus 4 would be 31. So we had to adjust the boundaries there. But the nice thing about adjusting the boundaries is then you don't have to plug this statement back in, so it saves you a step. Yeah. This is 2 ln of u such that 4 to 31, and we're going to do upper boundary minus lower boundary. So it's going to be, I always like to set that up, upper boundary minus lower boundary. So it's going to be 2 ln of 31 minus 2 ln of 4, whatever that is. And you would just keep that as your answer. The only ones you can do without a calculator are ln of 1. Oh yeah, you can factor out a 2. So that would be like this. Yeah, that means the exact same thing. The only ln's you can do without a calculator would be ln of 1, which, hey guys, what's ln of 1? Good, nice, that one's 0. And then the only other one you can do without a calculator is ln of e. Ln and e cancel, and so that would just be 1. The reason there's not a plus c for this problem is because it was a definite integral and we had boundaries. You put a plus c when there's no boundaries. If you have boundaries, you do upper boundary minus lower boundary and you get an actual numeric answer. This is a number, guys. Like, do you get that? Like, that's, you type it in the calculator. Like if you do 2 ln of 31 minus 2 ln of 4, you get an actual number. What does this number represent, guys? Like, what did we actually find? Like when you do a definite integral, fundamental theorem of calculus, like what does that number mean? Like what did we actually find? Think back to the beginning of unit 6. Oh, this is making me nervous that no one's answering. We don't know what a definite integral represents. Well, we did an antiderivative, but if you have actual boundaries from 0 to 3, what does this number represent about this graph from 0 to 3? Good, thank you. Okay, I got nervous there for a second. Is the area under the graph. It's the area between that graph and the x-axis. And if the answer came out negative, what does that mean about the area? Good, it means it's below the x-axis. Yes, good, below sea level. Okay, all right, cool. That made me scared for a second, but I think you guys have got it. I jogged your memory.